Hey, we talked about voltage and current now. Let's talk about resistance and other fancy things like resistivity and conductivity and learn about this dude named George Simon Ohm. That's George without an E at the end. So fancy. Okay, resistance is the opposition to current flow. That's a pretty easy concept. Just like kinking a garden hose causes resistance to the flow of water through the hose, adding resistance in an electrical circuit hinders the flow of current in a circuit. The equation symbol for resistance is R, and the unit for resistance is the ohm, named after George, without an E, because his last name is Ohm. Anyway, the symbol for the ohm is the Greek letter omega, and it looks like a pirate hat. Arg. Anyway, George without an E published a paper back in the early 1800s describing results of experiments with different materials. He found there was a linear relationship between how much current flowed through a material in relation to how much voltage was applied. He defined resistance as the ratio of voltage divided by current. This equation should look familiar. It's Ohm's law. We've talked about and used Ohm's law in previous videos. Usually we don't write it like this though. We normally write it as voltage equals current times resistance. This is a little misleading though because it seems like we're defining voltage in terms of current and resistance, which isn't the case. Remember, we already defined voltage as joules per coulomb. Ohm's law is actually defining resistance in terms of voltage and current. An important thing to remember for now is that Ohm's law isn't actually a law so much as an empirical statement. There are some materials where the linear relationship between voltage and current doesn't hold true. In fact, I just did an experiment video with a light bulb where I proved Ohm's law doesn't always work. You should check it out. Anyway, back to resistance. We say that 1 ohm of resistance exists when 1 amp of current flows through a circuit with 1 volt applied to it. Now let's talk a bit about materials. The resistance of a material, for instance a copper wire, varies with its geometry. Say we have 50 feet of wire of a certain gauge. Gauge is a fancy term we use to describe how thick the wire is. Well, copper is a conductor, so it has low resistance. But it does have some resistance, and that resistance would double if we doubled the length of the wire to 100 feet. In the same way, if we doubled the gauge of the wire and gave it twice the cross-sectional area of thickness, the resistance would be cut in half. Maybe think of it like a straw. A longer straw is harder to drink out of, like one as tall as a building would have more resistance. Or one of those tiny little coffee stirring straws that you stir your coffee with. Have you ever tried to drink through one of those? It's not so easy. If you double the width of the straw though, it's a lot easier. Coffee. But what about wire made of different material? How does the chemistry of the material affect its resistance? Well, this is where those fancy words, resistivity and conductivity, come in. Resistivity is defined as resistance times the cross-sectional area of a material divided by its length. Its unit is the ohm meter, and it's a way of looking at the inherent resistance in a material independent of physical dimensions. This way you can compare the inherent qualities of different types of materials, for instance, comparing aluminum to copper or silver. Aluminum, copper, and silver are all good conductors, so it might make a little more sense to look at these materials in terms of how well they conduct current as opposed to how well they resist current. This is where conductivity comes in. Conductivity is just the inverse of resistivity, and its unit is a Siemens. Potato, potato. There are tables you can look up that list different materials and their properties, including resistivity, conductivity, thermal coefficients, thermal conductivity and resistivity, and stuff. Honestly though, that's the extent of what you'd need to be concerned with. Say you're just curious how gold compares to Teflon as an electrical conductor. You would look it up in one of these tables. In practical application, you probably won't find a pressing need to use resistivity and conductivity, but it's good to be aware of what they are. Okay, in the next Learn Electronics video, we're going to be talking about resistors. They're the actual devices in our circuits that provide the resistance we just talked about. They set voltage levels and limit current. How fun! Don't forget to subscribe and hit that like button.
Smash the like button.
I'll see you in the next one. This is Life Me Lightning. Bring a little lightning into your life.